All right, so maybe I'll just go in the order of here. So Ted Rappaport is the founding director, or the messiah of millimeter wave. So maybe I'll just ask them quickly, to each of the panelists, to talk a little bit about what their organization is doing, and particularly their involvement in industry. So Ted?
Okay, I'm at NYU Wireless with my colleague Sundeep. As you know, in 2011 and 2012, we did the pioneering measurements that proved to the world that millimeter wave would not only work, but actually, as you'll see in my keynote tomorrow, works better than any other generation of cellular we've ever had, which kind of busts a bunch of myths about going up higher in frequencies. We've done channel modeling, we've done network access, we've looked at all kinds of things with 12 faculty and about 100 grad students here. And Sundeep, thank you, and Akbar, thank you for bringing the millimeter wave community here to NYU. We're really glad to have you and hope you have a great couple of days here.
I just also want to say Ted has worked extensively with industry, so we'll have a unique perspective. We've worked with many of the companies that have been founding in the millimeter wave space, and we'll have an interesting perspective for this panel. So Ozge is actually, I think, maybe senior director, is that right? Yes, at Qualcomm. He's been heading the entire millimeter wave effort when it was in its infancy in Qualcomm, so you're getting it firsthand from him.
Hi, my name is Ozge Koymen. I work out of the New Jersey office in Qualcomm. I'm part of Qualcomm research, so I'm not on the product side, but we interface closely with the product team. So we've been looking at millimeter wave for a number of years now, started in wireless backhaul, then started looking at the access part of it. Work with Ted and others on the channel measurements, channel modeling, proving it out, and then really went full into it, and you know, our focus really is to make this work in a UE handset. So it's not really a fixed wireless type of application, although we do look at that as well. But it's really in a UE handset, and that's what we've been trying to prove for the last couple of years, show that it is feasible, and we'll be heading to commercialization pretty soon, so that everyone here can also see that it works in a handset.
All right, next up is Harish Krishnaswamy. Anyone who's familiar with the millimeter wave as a circuit design knows a lot of his work out from Columbia. But I also wanted him to come onto the panel because he's involved in a very exciting startup and give his perspective from a small company in the field.
Thanks, Sundeep, and thanks to Sundeep and Akbar for organizing this. So my name is Harish Krishnaswamy. I'm an associate professor at Columbia University in the Electrical Engineering Department. I've been at Columbia for close to 10 years now. My group there works on RF and millimeter wave IC design. We try to innovate at the IC design level in the circuits for new forms of wireless communication in general. So we've looked at things like full duplex, massive MIMO, and of course millimeter wave. In fact, my history with millimeter wave goes back actually to the days of my PhD, starting in 2003. In the mid-2000s, actually, a lot of the fundamental circuits work in millimeter wave was done back then. We were looking at, can you push to higher frequencies? Can you build a multiple antenna system, phased arrays on a single chip? And at that time, the big excitement was around the 60 gigahertz unlicensed band that later came to be known as WiGig. But around 2009, 2010, that didn't really take off. And then in the early 2010s, as Ted pointed out, because of a lot of pioneering work that happened, of course, from NYU Wireless and other places, there's a lot of excitement now around cellular communications at millimeter wave and the so-called 5G. And so we've been looking at circuit innovations for that as well. As Sundeep pointed out, we recently spun out a startup company that is looking to commercialize some of this RFIC work, as well as incorporating some system concepts. So, happy to speak about that.
All right, and finally, Tommy Svensson, come from Chalmers University all the way from Sweden. He actually has a one-slide visual, if that helps.
Thank you for inviting me. So, yeah, I have a background I'm leading wired systems research at Chalmers, and a background also a little bit at Ericsson. I worked employed 11.5 years. I worked 2.5 there. I did my PhD on code modulation back in the end of the 90s. Well, I finished 2003. And then we worked on micro radio links up to 37 gigahertz. We had a project 2009 to 11 with Ericsson and a couple of companies where I worked on advanced micro radio links. And we started an online on site millimeter wave backhaul links project in 2011. We worked half a year in it, and actually we lost the funding, 600,000 euro. because the German funding is a bailout. Anyhow, we tried to start it there. But then I worked on millimeter wave communications in the big EU projects from 2015 to 17. So this picture is from there, a project we called Millimeter Magic, where we worked on waveforms, frame structures, cooperative hybrid beamforming, cooperative beamforming, and a couple of things. So with this slide, I want to illustrate a little bit what we are continuing doing at Chalmers. We have a research center called JSON, and 5 projects related to high-frequency communication, or high-frequency techniques for sensing communication. And I'm leading a project called Mantua. This picture illustrates a little bit that the scope we have, actually it's a PowerPoint, so can you step forward a little bit? I have some text coming up.
Oh, yeah.
So we have 4 web packages. We try to work a little bit academical here from fundamental, understanding what key performance metrics should we actually have to analyze from a communication theory point of view, taking all the way down to hardware and up to use cases, because I think we maybe should rethink a little bit. And then we work on different kind of architecture, how we should use the bits, where we should do the processing, and how many bits we should have in front-haul, backhaul situations. And we work on different cooperation techniques for access, and also with joint wireless access backhaul. Because in Europe, 56% of the links are wireless backhaul. And I see a convergence here. I think we should jointly design it. And then we also have some demo activities. We have test bed at 30 gigahertz called MATE, Massive MIMO Millimeter Wave.
Okay, great. And one of the other things I wanted to get Tomi to talk about here is they have a sort of slightly different model for the industry university partnerships in Europe, where there's a very close partnership on very large projects, and we can, hopefully that can come up into discussion. So Akbar started this session today with a kind of a quick history of what's happened in millimeter wave in the last few years, and it's been really dramatic. If you look back just in the last 5 years, you've seen a huge amount of progress. The FCC has opened up a large number of bands. You've seen a number of trials, and I wanted to start off with the panelist. You know, what have we learned from these trials? Ted wrote a very famous paper, millimeter wave, it will work. So is it working? What are the challenges? What are the research? And if any one of you want to start with, take a stab at that. Ted, maybe you're the one who wrote the paper, it will work. Were you proven wrong, proven right?
Yeah, well, what you're seeing in the popular press...
Is that coming on? Is that sound coming on?
Yeah,
okay,
it's on.
Okay.
The carriers are all reporting better than expected results. If you've noticed, and if you have personal talks with the people leading them, they're kind of shocked. In fact, we saw that at the Brooklyn 5G Summit. It's video recorded on IEEE, where we had Qualcomm and Intel both presenting their first generation chips at 28 gigahertz and marveling at how much better it works than they ever expected. So yeah, it not only works, it works better. There's more bandwidth. And as long as the distances are kept relatively short, that is less than a few kilometers, the weather impairments really don't affect the channel severely, such that the data rates are beyond anything anyone's ever seen in wireless. So it not only works, it works better than what industry thought, which is good news because it kind of opens up the minds of the general engineering community to realize that if you look at fundamental physics and try to apply things, you saw Dr. Chaffee's talk, the Sommerfeld equation, 1909. You know, millimeter wave was developed by Bose and others in Russia in 1890s. You know, finally, 100 years later, plus, we're seeing that it can change the world. So, yeah, I think it's working better, but we should ask Ozge that question because he's making the chips, and hopefully we'll have them in handsets by Christmas. That's my prediction.
Yeah, so it does work better than we expected, actually, and because it was 4 years ago when we started this project, we really had doubts, so that's why we started doing the channel measurements and working with NYU, and then quickly we realized after we built our prototype that it does work a lot better than we expected. So we weren't involved in any of these trials because these trials are really focused on fixed wireless. So our testing was really more internal. You know, we do have UE handset form factor devices and prototypes that we've been testing, and I can say that many people that do visit the New Jersey office, and we show them the indoor enterprise use case, for instance, and how it can work and how you can hold the device and try to hand block it and see the effects of it. Everyone that comes in, the operators or anyone that has disbelief in the beginning, and they just don't think it's going to work. And then we show them that it penetrates walls, it penetrates 30,000 square foot office, no problem. And we give them a challenge to try to block it, hold the device, try to block kill the signal, and it's not that straightforward. And actually, many people are surprised. So now, but that disbelief still exists. So there are many operators in the world and many companies in the world that still believe that it doesn't work, that still believe that it's not going to be it's going to be a failure, and due to the small propagation distances and density required, and all that is really will all those questions will be answered in the next 6 months or so, and as we start commercializing it, and we have massive trials starting at the end of the year with hundreds of handsets and wide area urban environments, and then the commercial handsets come first half of next year. That's when really we have to prove to the world that it does work. Until you have the massive deployments and the massive trials, people still have a doubt, and they think that things are engineered and they're presented in a way that it makes it look good. But we do have hope that we'll convince the world soon.
Actually, I just want to follow up on one of the things that you said. Is there a disconnect between where the vendors like Qualcomm are and the operators like Verizon? They seem that the operators still doing trials focusing on fixed wireless. Is there a lack of a compelling business case to go to mobility, or are they worried about the technical challenges with mobility? I know AT&T has claimed that they're also going to do a mobile trial, which is one step beyond what Verizon is doing, although I'm not fully sure if that's the case. So what are the vendors really the ones that are pushing the mobile part of this, but the operators are still at the fixed wireless stage? If any one of you want to try to take a stab, or go ahead.
Okay, I can. Yeah, so it really depends on the region and the operator, and which vendors are working with the operator, because some vendors don't believe in millimeter wave in a mobile use case as much as others. These are on the infra side, and on the handset side, we've been pushing it, and there are operators like AT&T and Verizon that see both. They see a fixed wireless and a mobile use case, and we're working with a bunch of handset vendors that majority of them do think it's feasible to put in the phone, and they are putting in a phone, but there are still some that have doubts, and maybe we'll wait for the next generation of it. But it really depends on the region. European operators in general don't see the mobile use case for millimeter wave, at least in the beginning. They're really more focused on the fixed wireless. And they've concluded that they're really, even for fixed wireless, in many places that there's no business case for it, that there's no need for it, there's no capacity need for it. So it's really the Asian and the North American operators that are the more aggressive, and they see the capacity crunch, and they see that this could really solve offload some of the data, that are really more interested in the handset mobile use case.
Yeah, in particular, I'd say KT, Freetel in Korea, and Samsung's a big driver for the mobile case immediately. And in China, that's where you see a big belief. Japan as well, NTT Docomo's coming along, but you really see Asia on the mobility. That's where mobility will happen first, I believe, and it'll happen within the next 12 months. You'll see mobile handsets and deployments of 5G mobile. But in the U.S., the landmass is so much greater, and the fiber build-out is tougher, as we saw, getting terabits to the last base station. So in America, it'll be a little slower, because they want to prove the technology, and they need time to get the massive fiber backbone. I think that's what the T-Mobile Sprint merger is all about, getting spectrum and getting enough fiber to be able to ramp quickly when you want to go.
Just want to echo, what's been said here in terms of what we as a startup company are hearing. I think both in the Europe and the U.S. we hear that So depending upon who you talk to, either we hear that there is a lack of a good business case for the mobile use case, or that if it comes, it will come later, and fixed wireless access will be what will come first. I think certainly Asia is the most bullish on mobile access. I think the other thing that we've been looking into is there a business case for a hardware vendor into fixed wireless access, basically? In other words, if you look at CPE equipment and access points for the fixed wireless access, are there enough volumes to justify, a custom hardware build out? And I think even that is a little unclear at this point. I think the amount of market penetration, historically infrastructure has been a more challenging space for custom hardware development compared to cellular. And the amount of market penetration that's projected over the next couple of years in the fixed wireless access, depending upon who you talk to, may or may not be sufficiently robust. So I think there are certainly business case questions even around fixed wireless access.
Is part of the difference that's coming between Europe and Asia and Europe and the US the fiber penetration? I know that was always a huge issue with the small cells, and of course millimeter wave is a small cell, or is it just that in Asia there's just a lot of let's say close relation between the vendors and the regulatory governments that actually basically pushing it aggressively? Tommy or anyone else, if you wanted to say something. Or any of the
yes, I cannot talk from company point of view since I'm at the university. But in Sweden, I can start there. Fixed wireless access, I think maybe it's not so important case because we have a lot of dict fiber. Although I think non-line of sight wireless backhauling should be an important case, and this flexibility with in-band backhauling, so you can start building out the small hotspots. Then where these hotspots should be. Personally, I believe in maybe professional situations, automation situations, where you can have a business case with a vertical industry. Maybe I could imagine that could be where operator can start earning money on millimeter wave. Then there seems to be a little bit split focus or a split view on the use at mobile cases. We have a big EU program work on connected vehicles called 5D car. Inside there, I see different views on it. Personally, I believe in millimeter wave is very useful for vehicles, and we can create better receivers. And we quite often have street canyons with more or less line of sight. Personally, I believe in that there's a good case there. But I also hear others being skeptical. So for Asia, I just remember when everyone said, okay, in Asia they're building fiber, I don't need any wireless backhaul. That was some time ago. But and they're easy to tear down houses and can build more fiber. That's not the case anymore. I think maybe 10 years ago we were rolling out 4G, that was the case. There seems to be interest in wireless for backhaul also there. And there's more friction to dig fiber. So I don't have a hands-on knowledge, but I just remember those comments some years ago.
Okay, great. I think we have a question here from the audience. You want to introduce yourself?
Sure. Dave Burstein. I write about this stuff. In fact, I just did 6,000 words on why almost nobody except Verizon in the West believes millimeter wave is going to happen soon, and I hope you'll prove them wrong. One of the answers that I haven't been able to find, and get lots of different opinions, is whether it's going to be practical to backhaul a millimeter wave small cell, which needs 5, 10, maybe more gigabits backhaul using wireless. What are you finding out? Verizon says they must have fiber, but it sounds like you think that you may be able to do it wirelessly.
I think Tommy had mentioned that there were like 56% of cell sites in Europe are already wireless backhaul. But
I remember my last application, that was 6 years ago, I think it was 54, 56%, we had some reference. That might have changed a bit, but in that ballpark.
That's a bit or less.
Yeah, for millimeter wave cells, if the cell sites were to increase, orders of magnitude with the millimeter wave, with backhaul.
Then I think it needs to increase. Personally, I also believe in, because we are working a little bit on hybrid fiber wireless, because I see maybe a migration path there. If you start to build out some millimeter wave access hotspots, maybe the business case is fully solid, so you maybe gradually want to add fiber.
Did you want to, Ted?
Yeah, fundamentally, there should not be a problem to provide high bandwidth, 10 gigabit per second plus wireless backhaul between small cells if the spectrum allocation is there. It's a very clean channel. There's high directional antennas that can be made in a small footprint. So physically, it is possible to be using small cell base stations for both mobile as well as providing backhaul from others, say several others. In fact, that's how I believe the networks will evolve. Small cells in an urban or suburban area will indeed have multiple antennas that can simultaneously steer to the mobiles while they, at the same time, have a dedicated steerable antenna linking the other base stations together. The key is having enough RF spectrum bandwidth, and the 28 and 39 gigahertz spectrum alone is not going to be enough to do that. So there's a lot of interest in terms of the carriers getting the FCC to release some of the spectrum up higher, 70 gigahertz and above. When you start getting these 5 gigahertz channel bandwidths, you'll be able to do amazing backhaul, fiber-like backhaul speeds at the same time you're supplying mobile.
By the way, I was really happy that Professor Chaffee opened this whole today's session with a great talk on the terabit copper. That was a fantastic talk, and maybe that'll also be a solution to small cells. That's always, if you've been in this space, you know that bandwidth to small cells have been always a key problem. Ozge, did you want to say something?
Yeah, so the backhaul part of it, so the fiber does exist in many of the base stations in Asia, so in cities like Seoul and Tokyo. In the U.S., it is a problem. So backhaul, you can certainly reach the multi-gigabit per second. It's really just what technology do you use. I mean, there are existing proprietary solutions now, which you can use, but the way we're pushing it is to eventually have the integrated access backhaul, which is being standardized in 3GPP right now, and that's something that we as Qualcomm are pushing with AT&T because we see the importance of it, and we see the importance of having backhaul and access share the same spectrum and dynamically allocate resources and have it be standardized so that we're not tied to a proprietary solution. So it's something that operators want, and it's really when that is standardized in Release 16 that maybe you'll see more deployments in a mass scale.
I think, Kate, you had a question?
Yeah, Kate Remley from NIST. Getting back to the mobility and the handsets, I guess I had been under the impression that one of the big impediments to deployment of handsets was the power consumption issue up at millimeter wave frequencies. And so it sounds like maybe there's been a breakthrough there. Are the handsets that you're talking about that are imminent, will they include the beamforming and the tracking of the base station and those kind of things? Thanks.
Yes. So they'll have multiple 28 gigahertz or 39 gigahertz RFICs with, what's feasible right now is just four antenna elements in each location. So it's a beamforming with a phase array, four antenna elements. So power consumption, it has gone, it's much lower than we initially thought, but it's still, I'm not going to say it's very low. It's still an issue, and just like the first generation of 3G phones or 4G phones, the power consumption might be a little bit higher than we want. But then the next generation of phones we'll bring it down further and further.
I want to let Harish chime in on this whole power consumption issue and then to Manisha. But on the power consumption issue, is there when I was looking at papers and then maybe the status has changed and looking at what industry was producing, there seemed to be a big discrepancy between what's reported in the top conferences in terms of power efficiency and then what people were actually practically obtaining in terms of power numbers. And the power consumption, I'm glad, Kate, you brought that up because it's been such a key issue as we're kind of moving past the functional phase of 3GPP. Do you want to?
Yeah, absolutely. So, I mean, I think when you look at what the numbers that industry has in mind versus what's in papers, as you said, there's definitely a discrepancy. And I think the discrepancy comes from both directions. So on one side, obviously, academic papers are going to be extremely aggressive in what they report as power consumption in various building blocks. You can easily report a very aggressive power consumption if you ignore several of the practicalities of what it takes to build a circuit that actually goes into a chip. A classic example is an analog to digital converter. The buffer that drives that converter and scales the voltage to full scale can often be the most power hungry thing in the analog to digital converter. But if you just test it with a signal generator that forces that signal in there, you can just take that power consumption out, report extremely low numbers. Also, the clock of a very high speed analog to digital converter can often be the most power hungry thing. If you play tricks with how you provide the clock, you can also report really low power consumption numbers. So certainly academic papers, we need to apply an academic correction factor in basically the power consumption. But also, I would say definitely, because this is early days in millimeter wave, I think what you will find that's happening in industry is some of the more basic and robust circuits being employed, and I think there is certainly room for innovation in improving the performance of the circuits that would be used in actual deployment. So there is basically a way for both sides to kind of come closer together. On this topic of power consumption in the UE, I think there's certainly improvements to be had, as Ozge mentioned. I think also we will hit some fundamental limits, though, in terms of power consumption. Power amplifiers at peak, a vanilla power amplifier would have an efficiency of around 20%, and under average, under modulation, maybe the average efficiency is less than 10% now, or early 10s at best. I think there's probably maybe a factor of 2 to be had there with power amplifier innovation through better power amplifiers, through linearization techniques, but it isn't going to go up 5x, right? You can never exceed 100% in efficiency. So I don't think there's 10 dBs to be had in power consumption, and so I think it's an issue both in terms of battery draw as well as thermal considerations in the phone. I think the way that we should be looking to make this work is to make the link even more asymmetric than it is, reduce the number of elements in the UE as much as you can through base station designs that have that get closer to the EIRP limits that the FCC allows you. So I would say, is it possible to do something with, just a 2-element array, for instance? I don't know that the directionality of the array is as critical as the power combining, but if you get benefits on the small cell side, can you actually relax the requirement in the UE? I think that's the way to make believers out of.
So kind of a massive MIMO you're proposing, really, that sort of topology in a way.
Even more elements on the small cell side, get more beamforming gains. The flip side of that, what people will ask is, well, what about the uplink, right? That helps the downlink. That doesn't really help the uplink if basically the UE is hobbling on 2 elements. I think at least initially, traffic is unidirectional these days. There's definitely a lot of interest in things like millimeter wave for supplemental downlink versus uplink. So I think that is, a viable way forward.
Manisha, before I just want to let Manisha get a question in.
Thanks.
Before you go, Manisha, I just want to follow on. I think Harish is exactly right. I think this is a really important point that the industry's not talking about, that the ability to put very high directionality in a very small form factor at the base station is going to be the key to success, because we're going to need that base station to do a whole lot, because with only 4 or 8 elements in the handset, there's not going to be tremendous uplink margin, so we're going to have to hear much better. And so this great directionality at the small cell base station is not only going to make the mobile link on the reverse link or the uplink, but it's also going to give the ability to steer and look at other base stations for this backhaul. I just wanted to amplify that point because it's a really important one. Now, Monisha.
Thanks. Monisha Ghosh from NSF. So actually, before I ask my question, I just wanted to follow up on the power consumption thing. It's also an issue at the base station. The numbers I've heard about how much, because of the nonlinearity of the OFDM waveform, and the backoff that you have to do, the amount of power these base stations are going to end up using is enormous. So aside from that, I wanted to pick up on something that you mentioned, and I'll play a little bit of devil's advocate here. You mentioned that you started working on millimeter wave when WiGig was hot. That did not take off, and so you switched to cellular. So what exactly makes, if you look at all the projections of where the high data rate is being used, it's indoors, and WiGig should have addressed that market. So what is the rationale behind saying that we did not succeed in WiGig, it's going to succeed in cellular?
Good question. Anyone want to take that tough one?
So I mean, I can attempt to answer that. I think there might be other people on this panel who are also Qualcomm, for instance, heavily invested in both technologies, can talk about how they view WiGig versus cellular. With regard to my point, I don't think WiGig didn't make it for a technical reason. I think WiGig didn't make it because it was a little early. There wasn't a good market need at the time. I think if you look at some of the first startup companies, so Cybeam was a startup company that started in 2003 when I was starting my PhD out of Berkeley. If you think about that, something like 15 years too early, right? And I think they were coming out with their first product in 2009 with essentially a 60 gigahertz. At that time, it was a different standard. It was called wireless HD, and they were coming out with those chips to be embedded in smart TVs. 2009 was not a good time to be coming out with a product that added $500 to your smart TV. So I think there was a little bit of a timing issue. I think also the applications hadn't matured at that time. If we look at what we think is going to require gigabits per second data rate now, I mean, really, if you want to have gigabits per second, it needs to be 4K video or above. So it needs to be really high definition video, and it needs to be an application where latency matters so that you cannot compress that video, right? So even streaming video, it can be compressed and basically sent over low frequency Wi-Fi today. So we really need applications which are ultra low latency, but also extremely high data rate, things like VR and AR. And I think, the 2000s was not a time where essentially those types of applications had matured. So I don't think WiGig didn't make it on a from a technical standpoint so much as just being a little early. But I really should let Ozge comment on how his team versus the Velocity team within Qualcomm sees their individual roles.
Yeah, so timing is a really big part of it. Right now, we actually are seeing more traction in WiGig now because especially with VR headsets. That is one application where latency matters and high data rates matter quite a bit. And so that seems to be probably the best use case for it. There really wasn't a use case for a handset or for a laptop too much. There were some projectors, I think, wireless projectors that came out. But the problem that the difference between the WiGig and the licensed 3GPP really becomes also what you can support. WiGig is really just focused on a point-to-point link in room, high data rate, but you don't really get, given their power targets and the ERP targets, and you don't really get penetration out of the room. And given that it's really intended to be a point-to-point, and each side is trained individually, it doesn't really scale in a mass environment. So there's, unlike in license where you actually broadcast your directional signals and all the UEs trained to it en masse, in WiGig it's really just a point-to-point type of thing. So it's very hard to scale it. So when you start deploying in bigger environments like convention centers, indoor stadium, then that's really not really well suited for WiGig. So it was really probably timing and also just a very narrow focus on what they really wanted to achieve that didn't allow it to take off.
I'm Jinfeng Du from Nokia Bell Labs. So the challenge you mentioned for the WiGig is not air interface. It's more mic issue, which could be addressed quicker since the hardware, if hardware is already there. So why not address the mic problem rather than develop a new set of air interface?
Well, I mean, at this point, both are ready, right? We have chipsets for both. So there's no need to go back and try to fix that. But the other problem with that is that they're just given their target of 2 gigahertz channels, and now they have channel bonding, and it's not really intended for long distance coverage and more. And the use case is just not there. It's really just there for in-room point-to-point type of links. So it's a lot bigger effort to take that and make it a more of an access type of system.
Yes, I just want to kind of amplify a point. 2 gigahertz channel bandwidths. I think some of the I don't want to say mistakes, but some of the challenges that one sees with WiGig is, 2 gigahertz is a fairly wide bandwidth. Often you don't have the signal-to-noise ratio to basically fill that bandwidth with, a high constellation. I think the standard would have done better to have a scalable bandwidth that allows you to back off to like 1 gigahertz, 500 megahertz, and those kinds of bandwidths based on the available signal-to-noise ratio that you have. So I think that would have been something that would have helped with the robustness of WiGig. My other perception with the use cases of WiGig that people were looking at in the mid-2000s is being completely indoor, you're really limited by the pipe that comes into your house, right? So if you're suddenly able to do multiple gigabits per second, if you don't have a multi-gigabits per second pipe coming into the house, then you're really limited to use cases where the source of the data and the sink of the data is inside that house. And those are starting to be, it's hard to come up with those, I think, VR and AR. That's why I think the traction that you alluded to WiGig getting right now is either AR, VR, or now suddenly outdoor applications such as the Facebook Teragraph project that Qualcomm is working on.
We had a couple of questions, one from Akbar, and then I'll get Damar one.
Okay, so before we left power efficiency, I wanted to ask, Ted mentioned, hey, we need to go to higher frequencies. And so one question is that how would these power efficiency issues that Harish and Ozge alluded to would scale as we go to higher frequencies? And the second one is someone mentioned, Harish or somebody, latency, app use cases. So millisecond latency was one of the things. How far can we even achieve it in any use case? And I want to hear something on latency.
I can come because I had a couple comments I want to do on the energy efficiency or power efficiency. I think we need to split the word a little bit also. Are we hardware limited? Are we energy heat limited? Are we EIRP regulation limited? And there are different solutions on the network level for that. I really believe we should do as bursty communication as we can, so we can have sleep modes when we don't have a very heavy pipe like a stream virtual reality. And then why not have some crazy academic ideas for the uplink? Virtual antenna arrays. Try to cooperate as often as we can and use some out-on-band links or resources for shared data, so we can get access to more antennas and get better beamforming gains. Then I have a comment related to how it scales. I know because we are working on Terahertz. It's called a FET flagship initiative in Europe now. I'm part of that. And we also have a lot of the people at Chalmers working on Terahertz components. And the heat management is the key problem from our perspective. So it's not scaling well. If you cannot have hydrogen or helium cooling.
This isn't a handset device or a
this is general chips try to create.
Just even the chip itself.
Yes, to make many, for example, many RF chains, because it's hard to get enough power from one chip. So if we could get massive parallel chips, but then the heat is one of the key challenges.
Let me say,
go ahead, sure. But then we'll try. Go ahead.
I'll be very quick about this. I just want to say something about the power efficiency that Akbar was talking about. So, for a given technology, a flavor of CMOS or a flavor of any other semiconductor technology, the rough rule of thumb is that output power and efficiency scale as 1/f. So if you go 10 times higher in frequency, both of them go down by roughly a factor of 10. But simultaneous with that, technology is getting better, right? We're getting newer generations of the semiconductor process. People are making improvements for millimeter wave. So I think just as Ted and Ozge talked about at the system level in terms of propagation and robustness, people are surprised by what they're able to achieve at millimeter wave. I think also we're seeing some surprising results from the efficiency of circuits, specifically power amplifiers. It's possible to get peak efficiencies of around 40%, average efficiencies around 20%. That's not so far off from what you can get at RF, certainly not an order of magnitude. That's point number one. I think point number two, I want to allude to something that Monisha was talking about, which is the OFDM waveform and nonlinearities. I think actually the biggest gains in efficiency to be had at this point are to get system people to talk to RF people more. So as an RF designer, I can tell you that after working with system designers within the startup, I now understand how horrendously underspec we make all our RF circuits. So we really assume the most stringent requirements at every single block in the chain, and then we proceed forward. And at the end of the day, you have an end-to-end system that is far more rigidly constrained than what you would need. So, for instance, my perceptions of the amount of backoff that you need for an OFDM waveform were at least 3 dB more than what you actually need. I'd say the standards have also been more generous towards 28 gigahertz systems than for the sub 6 gigahertz cellular, which is nice, right? We all need a little help. So I think bringing the systems folks closer to the RF folks are probably actually where the biggest delta is to be had in efficiency these days.
Okay, I think Marwan, and you want to just quickly introduce yourself and then.
Yeah, Marwan Kronos, University of Arizona. So going back to the issue of beamforming and the number of antenna elements that we can afford at the mobile and so on. So my question is related to this hybrid analog/digital beamforming, and since it's just been, at least in academic circles, it's being discussed extensively. How practical is this for indoor, and more critically, what are the implications in terms of power consumptions, if any? This is more on the signal processing side. Is this of a concern? Do we expect to see some form of hybridization to take place in indoor environment?
Yes, I'll talk about that tomorrow morning when I give my talk. But it's both very practical and will happen, not just indoor, but outdoor. And what we've seen is that you don't need all these very, very complex joint coordination of multiple base stations. That is kind of the ultimate in comp to achieve near optimal capacity. That is, as long as you do a little coordination and smart hybrid beamforming at each individual base station with a minimal of passing of information, you can do tremendously well. People are working at it in the companies. You'll see chipsets probably in 18 months that are implementing this, I believe. So it's very feasible, and actually hybrid beamforming makes so much sense because to go full digital with 16 channels or 8 channels is very expensive on the power side, but you can do so much less power consumption in a hybrid approach and achieve within a few % of what you would get in a digital. So yeah, that's going to happen. I want to get back to the question Akbar asked about latency, and something that I think is a really nice rule of thumb to just remember in this era. I call it the massively broadband era that we're now in, and I think we're here now for the next, for the rest of time. In this massively broadband era, radio waves travel 1 foot per nanosecond, and so to go 1,000 feet is a microsecond, and you do 1,000 bits at 1,000 feet, you're now at a millisecond. So a good way to think of 1 millisecond latency is 1,000 bits over 1,000 feet. And so if you have minimal or processing time of epsilon, we're talking about 800 to 1,000 bits in a millisecond. So any packaging of data in whatever bandwidth you have, whether you have a bunch of narrowband parallel channels or a broadband channel, really can meet that 1 millisecond latency. And so that's why you see the 5G standard in 3GPP having roughly 1,000 bits per transmission. So we're getting there, and it's just a question of the physical channel and where you're sending the information to. The biggest problem is the back end, where you're going to cache the data. And that's where I think there's very exciting work going on, and where you're going to see very interesting business combinations between Facebook and Amazon and AT&T and Verizon and the people that know how to cache data that's accessed at the back end. I think that's a very exciting part of the future of telecom.
I think Tomi wanted to chime in, and then we'll get it over to Stefano after that.
Just a small comment on, because of one key use case people talk about low latency is connected vehicles for maybe dynamic maps and mobile edge computing. And it's easy to be naive coming from telecom and go to another industry because it's very complex a vehicle. They have a lot of security service. So it takes seconds actually to reach their destination inside the car for this information flow, even if you are a millisecond of the air interface. So simply the problem is quite often bigger than we think from telecom side to get on the latency. That's a generic comment given from the automotive application.
Definitely. Stefano, just quickly introduce yourself.
Stefano Galli with Huawei. Going back to the comment about RF engineers talking more systems, but also comms engineers. Above 60 gigahertz, 3GPP has not defined the waveform yet. Would a single carrier millimeter wave waveform make life easier to exploit the low power efficiency of the amplifier, not having to back off or phase noise and things like that? And your opinion on that?
So I think the gap between single carrier and OFDM is not as severe as what people would have to would believe, right? So WiGig has actually migrated towards single carrier. No, in AD, nobody implemented the OFDM standard. In AY, everyone is kind of moving towards single carrier. But I don't think actually the gap between single carrier and OFDM in terms of the peak to average power ratio, basically waveform complexity, how much however you want to define it, is that significant. And I think we're seeing innovations in the hardware side that would allow OFDM. So, I'm personally a believer in OFDM waveforms. I think single carrier is leaving, is leaving bang for the buck on the table. And so, that's my take on it. Yeah.
Also, remember in the uplink, you can get a lot of the peak to average gains by using a single carrier waveform per transmit block, much like it works in the LTE. So it's possible that there would be even less loss, at least on the UE side, where you're not multiplexing as much. I want to just switch topics. I want to actually get back to some of these great technical issues, especially on the networking. But it was just last month that I think Akbar mentioned this, that the Release 15 3GPP standard came out, and congratulations to all of any of our industry folks who have worked on that and worked very hard and got an amazing spec out. I want to ask your opinion, a couple of points. Do you think of the new radio standard as really incremental or revolutionary? And so we're spending a lot of time in academia here working on this. Was any of it useful towards how you made the standard, and or are we just wasting our time?
That's for Ozge.
Certainly our interaction with NYU Wireless is, had a big effect. 4 years ago, we really weren't a believer, and we, I guess our interaction made us a believer. And then after that point, just given the way Qualcomm is, we kind of stuck to ourselves, and we contributed standards, without much collaboration with academia. But I think the standard itself is, at least on the millimeter wave side of it, is it's all new, right? There's significant novelty there, and given the amount of time that we had, the industry, it was really many all-nighters by everyone in the industry to really pull off, because there was so much new, and it's really on all aspects of it. It's not just the air interface part of it, but it's all the RF testing, the RAM4 aspect of it. It's completely new. And how do we test this thing? Is it always have to be OTA? How do we do this in a conductive manner? And it was really quite an effort. And in the result, the beam management aspect of it, and the managing link failure, all that, it's really all new. It didn't really exist, and it's really just so sub-6. You could potentially argue that it was more, just evolution. But on the millimeter wave side, there were a lot of hooks placed that really didn't exist before.
Okay. Tommy?
A comment briefly, given the European perspective, we have these big projects, collaborative projects, industry, academia. So it's a little bit indirect in that way, because there we build a consensus, and then the project cannot contribute to a standard to 3GPP. So it is individual partners that do it. So we don't know the tracing, but we know that the METIS project I was involved in, it had impact on the way of thinking and what millimeter wave could be used for and so on. And the mmW project, I don't know how much actually contributed to standard in the end. But just a comment on the indirect way of we working in in Europe. Then, of course, we have bilateral collaboration between academia and industry. For example, Chalmers and Ericsson, we have a lot. A comment on what I think is new and good in the standard, though, is the beam spaces and the flexible frame structure. I think those are two important novelties that are game changing.
Well, I think I have a related question, and I'll go back to latency. So, physical layer, we can calculate that. Ted, you put it very clearly. And, I was at a meeting at Mobicom last year or something in Salt Lake City or somewhere. And luckily, in the panel discussion, there was a panelist from Nokia in the panel, I'm not going to name, and one person from Nokia in the audience. And they were working on different parts of this standardization. One was on the networking side, and one was on the physical layer side. And I asked networking people, and he said, TCP/IP is a bottleneck. We cannot achieve it. It'll have to be some kind of a new, I don't even know what, a hybrid protocol. And I said, okay, is the standardization body talking about it? And he's like, well, are you guys talking? And, it turns out they were not talking to each other. So I'm going to ask Ozge, is there anyone who's actually taking the networking side seriously to kind of make it closer? I know in your question you mentioned that Google has recently proposed some new protocol. Yeah. So I want a discussion on that, because I think that's kind of like an elephant in the room that's not being discussed.
I think, just as on Akbar's, I think we have a poster up. I know some of my students have been working on Google's BBR, and maybe into some test we've done here at NYU over interdigital stuff with BBR. We can talk about that, but I'll let Ozge, who was asked that question, respond.
So I'll have to admit, I'm not talking to anyone on that side. I mean, there are groups in Qualcomm that are focused on that. It's really that. My particular project is really an L1 and a RF focused project, and we don't necessarily talk to those. I mean, we're all optimizing our individual ones, but there are people that do talk. So maybe I'm at fault here as well for not talking up the chain.
So I think Harish's comment was good, that people have to talk. So if industry people are not talking within their own silos, we are in deep doo-doo.
Well, the IETF is where a lot of this networking layer standardization is going with the enterprise equipment makers, Cisco and others. The idea of TCP/IP, it is tough as you get to these very high data rates because of the overhead. And so there's information-defined networking protocols and a lot of funding that the NSF has done over the last 5 to 6 years, looking at new ways that specify not an internet protocol address, but rather content address. So if you have photos or there's a downloaded application, that can exist many places around the world in different caches, and you simply access it by a network identification. Shiv Panwar has been working on that, I think, in the back. Shiv, do you have something to say about that?
Yeah, I'll get to you. So Shiv is actually, I mentioned on BBR, and Shiv has been looking at TCP over this, and we have another TCP expert here, Michaela Zorsi, in the audience too, so both of them can chime in.
Yeah, I just agree 100% with the gentleman who's raised this issue, is that the networking people are not talking enough with the Airlink people and vice versa. And a lot of the gains in the Airlink that we are discussing today, which we are rightly discussing, may not be fully actualized at the application layer without a full knowledge of how these protocols work and rethink of these. So, BBR, we found, which is supposed to deliver low latency transport, is not aware of the vagaries of the wireless channel underneath, and there are a lot of issues with it. So certainly, I think there's not enough communication about how things at the physical layer ripple up to the applications and vice versa, which need to be addressed.
With a question over here, and then just quickly introduce yourself. And
Kumail Heather from Rice University, and a little bit more about that networking aspect. So mobile sensing is also a very attractive application of millimeter wave, especially bringing it to the mobile side. And I really think that the way to sell it would be communication plus sensing versus communication alone. But has there been any standardization efforts, or what is the industry kind of perspective towards it? Any efforts in that domain?
Sorry, standardization efforts on which part?
Mobile sensing, like
mobile sensing.
Yeah, like indoor localization or mobility tracking with millimeter wave.
So this is what's local.
On localization.
Localization.
Sensing
Okay.
with communication, like sensing applications.
I mean, right now the focus has been in 2GP standardization. It has just been EMBB, the enhanced mobile broadband, and that's really been the only application for millimeter wave. And even going forward in release 16, so where does millimeter wave find a place? It's really integrated access backhaul. There's some kind of there's positioning, but it's really those applications. It hasn't really gone beyond that. Is there a place for millimeter wave in sensing or industrial IoT, or those are yet to be discussed and standardized?
I think, let me just mention that the 3GPP standard actually does have a lot of hooks in it, beginning in the LTE or maybe even earlier for positioning. There is a whole specification just on the positioning part of that standard. So for example, as you know, if in the LTE standard you have to keep timing alignment. So as a result, you know the relative time of arrival from the uplink, and that can be used for triangulation. And all those parts are in the standard. And presumably they'll leverage that if they haven't already in the millimeter wave, because you'll get it to that much higher accuracy with the higher bandwidth. Tommy?
Just more comment. Well, I think both that tracks, for example, joint communication and radar. There are research going on, for example, Chalmers also. But then I think there's another aspect, and that could be to harvest information from the communications. Ericsson have shown maps from the micro radio link networks where they do weather forecasts better, with much better accuracy than the radio stations that were deployed. Because the micro backhaul network is so dense. So just by following statistics on the rain fading statistics, you can do better weather forecast. Well, when it comes to the moisture, at least, for the rain.
And I'm sure you've probably seen, Google has a project called Soli, which is using 60 gigahertz for gesture recognition. So they've been using just commercially available 60 gigahertz chips, converting the comm system into a radar system effectively. And then they've shown how you can use it to, for instance, on a smartwatch, scroll through things, swipe things, and so on. So I think it's clear that millimeter wave will always be a very high resolution radar. And I think, to what he was saying, there's definitely been work on repurposing communication, both waveforms and hardware for radar. So there's work on OFDM radar, for instance, which goes away from the more traditionally used waveforms, which might be, linear frequency modulated chirp or something like that. So I think it's definitely an interesting area for research.
You remember, actually, already we've seen on the automotive space going up from 24 gigahertz to 77 gigahertz. That's a big area right now, and put a pitch in for Harish has also built some very, I believe, even higher frequency radar systems in his lab if you were to head over there.
Just a question. So I'm curious about the views of the panel on 6G. So I personally think it's early to talk about that, but I've seen it's already, the academia it's been pronounced. So I guess NYU has a project on 6G. I've seen an article on that, and last week I've seen VT magazine called for papers on what will 6G be. Do you think it's early to talk about that, and what may be some fundamental technologies? So from 4G to 5G, there was millimeter wave. Is there anything new for 6G if we start talking about that?
Yeah, great question. I mean, I know the industry is just trying to catch its breath from that sprint out to release 15 on 5G, and it's now people are talking about 6G. Too early, or?
No, not for academia. That's our job in academia. So actually, I'm very excited about 6G, even though we don't know what it is yet. But it'll be faster, better, maybe not cheaper. But the fact is, I think 6G, I'm going to talk about it. I think it's above 100 gigahertz RF bandwidth, RF carrier, and 10 gigahertz plus RF bandwidth. And think about what you can do when you start to look at channel bandwidths of 10 gigahertz. Remember, a foot per nanosecond. 10 gigahertz is a tenth of a foot. It's an inch. So now you can start to think about, in a mobile device, in a chipset, the ability to get resolution to an inch, and actually with some simple signal processing, get fractions of an inch. Right now, how many of you use the camera on your smartphone to take a picture of something that's hard for you to see, maybe in the back of a stereo cabinet, or if you're like me, your eyesight's going, so you take a picture of something? How many people have done it in the room? Use your camera. Okay, so it's about 10%, and most of you are older rather than younger, with the exception of Kate. But the fact is, I think this is a glimpse of the future. I think 6G is going to bring this idea of using these very, very wide bandwidths to allow us to use our mobile device to see in the dark, to see behind walls, to actually bring radar and imaging and sensing to our handset and to glasses. And this idea of getting super resolution of the environment around us is something we really haven't done, but we will. And I think you get free spectroscopy. You know, if the air is bad, or there's a gas leak, or you know, you have an allergy, you're going to actually be able to monitor food allergies and your whole sensory existence in the world. I think 6G is going to bring that, and those are some of the exciting things that I think we should, in academia, should be working on.
Yeah, I think for industry, it's too early. We haven't even deployed. I think if I ask for funding, I have zero chance. Yeah, I think we'll just maybe in another 5 years or so.
But I mean, the good thing is that there is, federal funding for this. So there was a large center that was announced that is being led by the University of California at Santa Barbara and NY Wireless, and my group at Columbia is also participating on that center. The good thing about looking at frequencies above 100 gigahertz is when folks tell you that it's impossible, then obviously there are fundamental challenges to be solved, and so there's work for academics to go and do. So that's looking at new device technologies, so looking at 3-5 compound semiconductor technologies, whether it's indium phosphide or gallium nitride, trying to push them beyond 100 gigahertz, looking at how circuit and system design would change as you go to these extremely high frequencies. The bandwidths are now enormous. I think it will start to stress parts of the system that we, maybe took for granted before. Things like serial links and so forth will become extremely challenging. And then, of course, there's the applications, right? What can you do with enormous bandwidths, but you're now at very high frequencies, and so propagation is challenged. So I think there's definitely a lot of interesting work that this will force us to think about. And I think in Europe as well, I've certainly heard a lot of 6G type news coming from different parts. I think in Finland, I think the University of Oulu has a very large grant, that puts what we think of as large in the U.S. to shame, essentially, to work on 6G type technologies.
Yes. Well, from the start, I think these labels are sometimes a buzzword to be used for our own purpose. I remember when they started working on 4G in the winner projects, the operators refused to talk about 4G. No, we want to protect our investments, call it beyond 3G. So we did that in the beginning. And before the end of the fourth-year project, the operators were keen on talking about 4G more than the vendors at one point. So it's a flip coin when they see the need for a new labeling of the new technology and the new visions, new things you can do. So with that said, I think there are a lot of things we need to do on evolved 5G. Actually, we have a workshop at Globecom. That's the series that I call them Technology for 5G, and this year we call it 5G Plus. There are a lot of things that need to be done based on what we have. Dense networks, closer to vertical application needs, non-standalone millimeter wave networks. I see things that sure you have enablers in the standard, but that's like basic ingredients for making the dish. You have the potatoes and the onion and so on, but you don't really know how to do the dish. If you go to a Michelin 3-star restaurant, sure, there are actually some knowledge behind the basic ingredients up to the dish. Then I also believe there are new things we should do in 6G, and as I mentioned, I'm part also of a big terahertz initiative in Europe now, and I sincerely believe there are things we can do there. From communication perspective, definitely backhauling, wireless backhauling. It's an easy case. We should move up and get the fat pipes to the base station using terahertz, and we can, if we get the hardware. Please. But then I also believe in I really like what Ted said. I think there will be maybe more similar focus on sensing and communications in the 6G era, and maybe also computing in the same pool. Maybe we should do all three at once, because time matters, energy matters. I mean, delay matters, NA matters in those contexts. So definitely there's a need for 6G. Although they're taking the labeling race a little bit. To be honest, I don't know if I think there are so many new things there. But I believe there will be 6G, and terahash will be a component.
All right, and we have about 10 more minutes left in the panel. I want to kind of switch to two meta questions, really. The first is, now that we have an industry panel here, is about what's the role or ability for startups to get involved. One of the big problems in the cellular space in general has been the huge barrier to entry. I know you're involved in a startup. We have Professor Chaffee here, a serial entrepreneur, and Ted. All of you have worked in this space. Can you share experiences? And is it possible? I know a lot of the students here want to get into startups. They all tell me this, but then they just really struggle. How do you get past that barrier? Is it possible?
Can I add to one thing to it?
Oh, yeah.
Sorry. That, going forward, 6G startups, that what is I also feel that as we go to higher frequencies, analog and digital interface is going to shift. If you look at optical systems, a lot of it is done analog. And there's a lot of techniques from there to be looked at too. So as you're looking at going forward, maybe comment on that too, where startups or technology could come in.
So, I mean, let me quickly comment on that as a sort of a little bit more of a technical question, then I can talk a little bit about my experience with a startup. So, I think when you go towards hundreds of gigahertz, we need to really start thinking about that analog to digital interface. It might even become similar to optical, where you sacrifice spectral efficiency for power efficiency. So instead of trying to do some 64 QAM or 256 QAM over 20 gigahertz of bandwidth, there have been people who have been looking at even just doing OOK type waveforms, non-coherent OOK. You still get 20 gigabits per second or more, but it's much more power efficient because you don't even need an analog to digital converter anymore. You don't even need a PLL anymore. It literally becomes almost like an optical transmitter, an optical receiver. So there's certainly a case for that, although that needs to be looked at in the larger system context, whether that would make sense. From a startup perspective, first off, let me preface by saying, don't get me wrong, I still wish I knew how to write an app like LinkedIn or something like that and make $1 billion, right? So I still wish that was my domain of expertise, and this will never be that. And so let me preface by saying that. But that being said, as someone who knows how to design circuits and make hardware, this is at least a time where there's a lot more openness. So the things that Ozge said about the standard being completely new, about there being this whole aspect of beam management that didn't exist before, we're finding that firstly in terms of raising money, and then after that in speaking to customers, they're a lot more willing to listen now, in this 5G I think we're sort of approaching the peak of the hype cycle of 5G, and so people are willing to talk to, emerging players a lot more. People are willing to listen to new stories that need to be told. So it's definitely, I shudder to think about what it would be like to try and sell a 4G, some new hardware for 4G or some new system for 4G to people. So it's definitely a lot more open. There's still always going to be, the challenges of breaking into, even if it's the cellular or the Wi-Fi space, maybe the Wi-Fi space is a little better, to a space which is dominated by the Qualcomms of this world right here, where also the number of potential customers, if you're talking about infrastructure vendors or carriers, are still only around 5. So I think there's certainly challenges, but this is probably, if you wanted to do a millimeter wave startup, this is probably the right time. I think 3 or 4 years from now will be too late, and certainly 5-6 years ago was too early.
Do you want to go? Always. You can always do startups. Great opportunity. Every time, every place. I've done 3 startups, sold them for $5 million, $40 million, and $3 billion this year to Verizon, straight path. They wanted spectrum. The fact is, there's always a need for good ideas, and if you can solve a fundamental problem and you're ahead of the market, you heard Ozge say that industry is so focused pulling all-nighters just to meet the next standard 6 months or 12 months in advance. They can't look further than 12 months down the road. So if you can solve some of the fundamental problems and be there and prove it and be tenacious. The real thing is being tenacious. I remember when John Chaffee was selling DSL. We were both young professors. I remember how hard he worked, and I saw him going to every single carrier, convincing them that you could actually do these data rates over copper. And he was there ahead of the internet curve, right when bandwidth was starting to ramp. Similarly, straight path with spectrum at 28 gigahertz ahead of the 5G curve that Verizon needed because they were behind AT&T in having the carrier licenses to deploy in the U.S. As long as you've got a really good idea and are savvy and really become a student of the game and talk to customers and listen to what's needed, you can always do a startup. Now, there are some startups that are better than others, more capital intensive than others, more likely to succeed than others. But, you know, there's always an opportunity. And just look at what's happened in millimeter wave. Look, if we were all in this room in 2012, 2013, even 2014, none of you would have ever thought that in 2018 there'd be a millimeter wave standard in a handset. You said it yourself. No one ever believed it. So, you know, someone with a good idea and with proof and tenacity, you can do it and you can change the world and you get paid for it.
Yeah, I think in millimeter wave there definitely is an opportunity because I just know from just our internal development that there are a lot of open issues, open holes, and you know if you're competing on the modem side of it, that's a brutal battle. Like it's you know, I think there's no room for that because of the Qualcomm and Intels and HiSilicons of the world. But on either end of it, on the RF side, there's a lot of innovation that can happen. Maybe the challenge right now is that interface between the modem and RF is not really standardized right now. So if you want to get into a handset, it's all proprietary interfaces. So maybe that'll change at some point. And then on the other side, on the upper layers, all the management of the interference management and enterprise deployments, and how do you actually deploy these millimeter wave systems? That's another software aspect that's open, and I'm sure there'll be innovations there as well.
Let me just wrap up then with, sorry, go. Just quickly introduce yourself.
Ahmed Suleiman from Embry-Riddle Aeronautical University, Arizona. I remember like 10 years ago when we were talking about WiMAX and LTE. WiMAX was supposed to be unlicensed deployment, and it could have given startup opportunity to be able to launch something if they really don't have the means of acquiring spectrum. Now my question is that, is the following. In the context of 5G, people are bringing in unlicensed bands. How much of that are you pursuing, especially Qualcomm and others? And will you tell customers that these services are provided over unlicensed band? So, because if you don't, then it looks like we bring in WiMAX from the back door.
So actually, this time around in 3GPP, shared spectrum unlicensed is one of the key topics, at least starting release 16, and it's something that Qualcomm actually has been pushing very strongly. We were key in doing the deploying. We did multi-fire on unlicensed LTE in the 5 gigahertz band. So there's, we definitely feel there's a room for that in the 37 gigahertz or 60 gigahertz deployments as well. And it's because of, it's a tricky balance because the operators, of course, they want the license, they want to control it, but then there are other non-incumbents that want to deploy if it's just a private network or someone like a Comcast or someone that wants to come in. We want to enable those players as well. So unlicensed is key in standardization as well.
Yeah. In fact, I would say if you look at the unlicensed spectrum, it's probably one of the most amazing low-capitalized success story in the history of telecommunications. Your cell phone in New York City is likely to be captured if you have Wi-Fi by the Time Warner cable or a Wi-Fi network. This aggressive access to all your Wi-Fi when you're in big cities. In fact, you have to turn Wi-Fi off to get it work if you're not a Time Warner or Comcast subscriber. I mean, they have access points all over, and it's amazing. You talk to the cable companies, and they are really seeing this unlicensed Wi-Fi entree to the world of mobility. And frankly, it's very symbiotic for the carriers that want to offload as much data as they can to keep their network keeping up with the 50% per year consumption of each human in the industry. So Wi-Fi will continue to grow. You're going to see WiGig is already happening now in enterprise. So WiGig is really starting to ramp. Qualcomm's going to see that. You'll see the chipsets that's really grow, and the phones will soon have them. So that all these outdoor Wi-Fi that the cable companies are providing will start consuming this higher 60 gigahertz and above. So they will always continue to grow, and they'll always continue to develop, but there'll always be a disconnect. And as much as people want to try to merge the two, they're just very different. It's not just the Mac, it's the whole infrastructure and the business model, and using enterprise indoor versus mobility. And mobility is the key to why 3GPP doesn't pay much attention to the unlicensed.
Okay, I think we just have time for one last question. Just quickly introduce yourself.
Ali Cafer Gürbüz from Mississippi State University. As several people mentioned, actually, millimeter wave frequencies are also very attractive for radar applications, higher bandwidths, better resolutions. You also mentioned like millimeter wave communications will be better if you get more bandwidth from the same frequency. So in terms of spectrum sharing, how do you see the feature of this in the same frequencies, radar or communication applications working together? For the industry, do you want to share these frequencies with the radar applications? What's your take on that?
Sorry, and just before you answer that, maybe this is we're running out of time right now. So maybe just if you want to either answer that or just give your final parting thoughts about how to help universities and industry come together and realize great products. End it at that.
I think so radar, I know our automotive division looks at radar, and they certainly wouldn't want to share it with the communication, because it's these are very safety critical applications. So I don't see that being shared. I mean, the sharing will happen more communication system to communication system. We might share with the satellite, we might share with other comm systems, but I don't see sharing with radar.
I think sharing's a tough sell when carriers are spending billions of dollars on infrastructure and spectrum. And you get maybe 3 dB. I think Michel Zorzi published a paper on sharing a couple years ago. The gains just aren't that great for the risks. Parting thoughts, this this broadband era, this massively broadband era is very new. It's really the sky's the limit. We saw a keynote today about a very exciting application of, plastic that's buried in the ground carrying terabits of data. I think it's a very exciting time to be doing research, and there are so many problems to solve. You've heard some of them this morning.
Yeah, the next year is going to be a very exciting time. We've really been working as an industry for the last, in academia for the last, 4 or 5 years to bring us to where we are today. Starting end of this year when we have these mass scale trials and we have the first handset coming out next year, it's really the fruition of all that hard work. And I think it's going to be an exciting time. And there are still a lot of open issues that industry and academia have to solve, and we'll only make this better and better, but at least now it's becoming a reality.
I think back to, I started at Columbia in 2009, so I was just coming from a PhD that worked on millimeter wave phased arrays. I started at Columbia in 2009. Nobody wanted to talk to me about millimeter wave for about a couple of years. They just didn't want to hear it. WiGig was a failure. I started to work at RF, actually. I went back to like sub-6 gigahertz. It was also, way less expensive in the lab to do that. That's a different story. But and then suddenly, 2010, 2011, 12, 13 came along, thanks to the work of, TED, NYU Wireless, folks in industry. The interest in millimeter wave exploded. Now there's more money in millimeter wave than academics know what to do with necessarily. So I think resources-wise, doing innovative work, there isn't there's a lot of excitement. There's a lot of willingness to invest, and so I think it's an exciting time from that perspective. I think the main wish list from the academic side of things, if I were to think about it, is I think there needs to be a stronger connection between industry and academia in terms of informing academia what the real problems are. On the RF side of things, as I mentioned, certainly a lot of work had been done in the mid-2000s. Of course, there's still open problems. I think power amplifiers are still an important problem. But I think really a lot of the open problems are the intersection between the hardware and the systems. And I think that's where each individual community is not necessarily sufficiently educated as to what the real problems are. And so I think think meetings like this are certainly very valuable. I think the different communities need to speak to each other so that we're actually solving relevant problems for millimeter wave moving forward.
I can comment on both the unlicensed aspects, I think, and a little bit on the research ecosystem. I think it's so important to have the unlicensed spectrum domain for innovation. A small company can start ideas, and so we really need to maintain and protect it. When we go up on terahertz frequencies, there are not much spectrum allocation now, but we need to protect in the ITS domain. I think there are room for innovation. There are ITS bands. They are dedicated for ITS services, but within that, it's unlicensed, right? Or you can have open competition. So it's very good there, but then at one point, when they scale up and become massiveness, we need to rely on it. We need the reliability of a license. So I think we have a decent balance as it is now, to be honest. On the research side, I can comment a little bit from EU perspective. Going from FP7 to Horizon 2020, the risk program we have now, it went from academic point of view, I think, a little bit too close to industry needs. There were less room for academic initiatives in the EU projects, in the bigger ones in particular. Let's see if it will be rebalanced. We have a new program coming up soon, FP9, and there will be, part of it at least, will be based on missions. So it will not be, everything is not decided, but the indications are there. Meaning that it's not so disciplinary research, it's towards problems, societal problems. So let's see if we will have clear dedicated communications programs. It might be connected to some missions. Let's see how it will go, but there's some new thinking there.
Okay, I want to thank the panelists. I also want to thank NSF, and in particular, Tiago Nandagopal and now Monisha who's here, because I think they were not just champions of 5G, they're the sponsors of this event, not just champions of 5G and millimeter wave, but also really, they both came from industry of trying to get industry and academics together, and so this kind of panel wouldn't have been possible without them. So hands of applause for all our great panelists. Oh.